We've previously defined kinetic energy as the energy of motion, and we think about that as like the energy of motion of a car, or the energy of the motion of yourself as you're walking, or if I throw a ball or something, that's got energy because it's moving. It extends down to the atoms and molecules that make up a thing, and we characterize how much kinetic energy the atoms and molecules inside a thing have with a quantity we call temperature. So in this module, we're going to be exploring thermal energy and heat and some of the, frankly, unfortunate aspects of how the universe behaves when it comes to getting energy, because thermal energy is going to be sort of the garbage bin of energy. It's where any process that is not 100% efficient energy goes into thermal energy, and the thermal energy is not easily captured, as we'll see throughout this module. So first, let's just talk about what it is we're actually, let's define what it is we're actually talking about with thermal energy, and it's also called in the textbook internal energy. That just means it's the energy of the constituent parts of a thing. So my pen is at room temperature. If I put it in the freezer, it would have less internal energy after it cooled down because the atoms and molecules that make it up would not be vibrating as rapidly as they currently are. So there's just energy in this thing just by virtue of it sitting here. And that's thermal energy, and since it's inside the object, it's also called internal energy. So examples of this are anything that's warm. So if you cook something in the kitchen, you're putting energy into it, and that causes the atoms and molecules of that substance to move more quickly. So let's imagine two different kitchen scenarios. In one scenario, well, let's just take one scenario. You're making chocolate chip cookies, and those chocolate chip cookies are on a cookie sheet in your oven, which is heated up to 350 degrees Fahrenheit. So you have put thermal energy into those cookies and into the cookie sheet that they're sitting on. And when you open up the oven to take them out after they're done, you can stick your hand in the oven, and as long as you don't touch anything, while your hand will be quite warm from the warm air in there, and you wouldn't want to leave it in there a long time, you can stick your hand in even without any covering on it, and you would not burn your hand. But if you touch the cookie sheet, even for a split second, your skin would burn, even though they're both at the same temperature. And the reason for that is that there's more energy in the cookie sheet than there is in the air because there are more atoms in the cookie sheet than there are in the air. It is more dense. And so the temperature tells us how fast those things are moving, but it doesn't tell us how many of them there are. And that's the difference between the internal energy or thermal energy and the temperature. If I have 100 atoms moving around very quickly, that'll be a particular temperature. If I have 10,000 atoms moving around at the same speed, they would have the same temperature, but there's 100 times as many of them, so there would be 100 times as much energy. And so that greater amount of energy, if it's transferred to your skin, would burn you. So internal energy or thermal energy is the kinetic energy associated with the motions of the molecules or atoms in an object, and we characterize it by temperature. If the temperature is a small number, that means those things have a low kinetic energy, they're not moving very quickly, and if they have a high temperature, that means they have a high kinetic energy, they're moving quickly. Um, the we're going to get to how we measure temperature in a second, but the other word I just wanted to highlight here is the word random, that these things are not, if all the atoms and molecules in the pen were moving in one direction, that means the pen itself is moving, and that's the macroscopic kinetic energy that we're familiar with. These motions are in every which way in all sorts of different directions. It's going to be very important to understand Heat and thermal energy, for one thing, we need heat to stay warm in the winter, and we deal with thermal energy as well when we're cooling things off. We're sort of running a heater in reverse. But also, anytime we generate electricity from fossil fuels, we are using the kinetic energy of something like steam that we've produced by boiling water. We're using that thermal energy, and as we will see, we cannot get 100% of that into useful energy like electricity. And so a lot of it ends up being lost to the environment. And that's what you see in this cooling tower here on the slide. Uh, Lots of times people associate these towers with nuclear reactors, but any kind of reactor that is boiling water to produce steam to turn a turbine, the water that comes out the other side is still hot and it's steaming hot. And so they put it in these cooling towers. It's unfortunately not hot enough to run the turbine, but it's too hot to safely put back into the environment. It'll kill the plants and animals that live in those bodies of water. And so we put it into a cooling tower, and the process of evaporation that you see with steam coming off cools that water off until it's safe to put back into the environment. So let's just briefly talk about temperature. Temperature is the number that we use to measure the kinetic energy of the molecules in the substance. It does not tell you how much thermal energy is in the substance. It tells you the average thermal energy of an individual particle in that substance. And to know the total thermal energy, I have to know how much stuff there is. So as we'll see as we go through this module, you need both the temperature and the mass of the object, as well as some properties of the object that tell us how easily those atoms or molecules move around. So the picture here, figure 4.1, just illustrates in low temperature, the little atoms here are moving slowly, indicated by the short red arrows. And if they are hotter, indicated by a higher temperature on the thermometer, they're moving more rapidly, but notice that they're moving in random directions. Now, I have my notes here for one purpose only, and that is to talk about temperature units. So the SI unit for temperature is something called a Kelvin, named after the British physicist Lord Kelvin. And it's not technically a degree, so we don't say degrees Kelvin, we just say kelvins. That's just semantics and not very important. Uh, this is the basic unit of temperature because remember, if temperature is a measure of the kinetic energy of atoms or molecules in a substance, higher means more kinetic energy, lower means less kinetic energy. Well, then what happens if the atoms or molecules are not moving at all? They have zero kinetic energy, so their temperature should be zero. And Kelvin, the Kelvin temperature scale, is the scale in which zero means the atoms and molecules are not moving at all. They literally have zero kinetic energy. So this is called absolute zero, and that is 0 Kelvin with a K, and that means no atomic motion or molecular motion at all. As a practical matter, it's very, very difficult in a lab to get anything close to absolute zero. Even the background radiation, leftover radiation from the Big Bang, has a temperature of about 2.7 Kelvin. So that's why that's our natural unit of temperature. Now, the units that we're used to dealing with when we're cooking or talking about the weather, we have degrees Celsius and degrees Fahrenheit. And the Fahrenheit temperature scale was meant to be 100 at the normal body temperature of a person, but kind of missed the mark a little bit. And the 0 degrees Fahrenheit was meant to have something to do with the weather in Germany, where Fahrenheit came up with this. Celsius is at least based on something a little bit more physical. 0 degrees C is the freezing point of water, and 100 degrees C is the boiling point of water. And happily, the Kelvin temperature scale uses the same size increment as the Celsius temperature scale. So on the figure here, you can see that on the left two thermometers on the Kelvin scale, at 273 Kelvin is 0 degrees Celsius, and 373 kelvins is 100 degrees Celsius. In other words, a change in temperature of 100 Kelvin is equal to a change in temperature of 100 degrees Celsius. They are just offset from each other by about 273 degrees. So 0K is minus 273 degrees C, but I only ever have to add or subtract a number to change from Celsius to Kelvin and vice versa. For a lot of the work that we're doing and in some of the assignments and problems that you'll be asked to solve, we're going to be dealing with temperature changes. How much colder or warmer is one thing than another? What's the temperature difference, which we will indicate by delta T? That's a change in temperature or a temperature difference. And delta T in degrees C is equal to the same delta T in Kelvin. In other words, if I'm going to heat something up by 10 degrees C, by definition, I am also heating it up by 10 kelvins and vice versa. That does not apply for Fahrenheit. You can see the somewhat awkward formula that converts from Fahrenheit to degrees Celsius on the slide here. You don't need to memorize that formula. We're going to try to avoid Fahrenheit as much as we can. Not only is it offset from the others, but also the size of the degree Fahrenheit is different than the size of a degree Celsius or a Kelvin. So the change in temperature, I don't have to do anything if I'm looking at a temperature change between Celsius and Kelvin. But if I'm looking at actual absolute values of temperature, which we will also be doing for some problems, then you do need to do this offset to convert from C to K. You just add 273. To convert from K to C, you subtract 273. But really, the one that you'll mostly be doing is converting to Kelvin, because that is the real physical unit of temperature. And for problem solving, that's the one that we're going to want to be in. But if the problem has a delta T, then there is no change and you don't need to worry about any conversion. If you did your conversion, you'd be adding 273 to both numbers, so the difference between those numbers would stay the same.